Welcome back to linear algebra. Let's jump into Anki. Right. Here we go. All right. What condition must be satisfied for the matrix A to have an inverse? And what is the inverse in that case? So A is A, B, C, D. So to have an inverse, AD minus BC must not equal 0. The inverse in that case is 1 over AD minus BC times the matrix C, negative B, negative C, sorry, D, negative B, negative C, A. What must be true of the diagonal entries for a diagonal matrix D to be invertible? They must all be non-zero. What is the row column rule for computing AB sub IJ? Row column rule. So we're looking for A times B at IJ. We're going to take row A times column B. We're going to take row I of A times column J of B. Multiply row A of I of A, by column J of B. Sum the products. So that was implied. How is the transpose of a product of matrices related to the transpose of the individual factors? Transpose of a product of matrices, okay. It's equal to the transpose of the individual factors in reverse order. The product, that is. It is proved in the text that the inverse of an invertible matrix A is also invertible. How is A related to the inverse of A is equal to A? If an invertible diagonal matrix D has diagonal entries D1, D2, comma, or dot, Dn, what is the inverse of D? It's basically a diagonal matrix with successive diagonal entries of basically 1 over D1, 1 over D2, 1 over dot, 1 over Dn, or the inverse of D1, but assuming, I'm pretty sure, it might not be correct there, but we're just going to say it's fine because assuming that these entries are numbers, the inverse of a number is 1 over, so that number. How might you express a solution of a linear system as an ordered n-tuple? That's supposed to be off. Parenthesis S1, S2, dot, Sn. Why is that? It is off. I don't know why that's on. X equals parenthesis S1, S2, dot, Sn, where the S's can be plugged into the variables of the system. Okay, well, it was, just S1, Sn, or parentheses, within parentheses, S1, S2, dot, Sn, good. All right, I'm going to continue working then on the latest problems, and then I'll be back to recall how I did in a little bit. All right, I ripped through some problems here. Finished up this problem. Finished up 43, which was about reflecting over xy, xz, and yz planes. A given vector 1, 2, 3. And then 45 was given these two transformations, find the standard matrix, and I was actually pretty happy that I was able to figure this out. What I did was use this additivity property. I believe that's additivity. I'll have to remember what homogeneity means then. But I think this is additivity. So basically what I did was take two of these. So t transformation of 2 equals this plus this. So 2 over -4. And then I took this transformation minus this transformation to find that t of 0, 1 is -4 and 9. So that means that this is a standard basis vector. So we know that the right side of standard matrix 2 by 2 is going to be this. And so we can just plug A and B for the other two. And then we can times it by this matrix equals this matrix. And then solve for A and B. And there we go. There's the standard matrix. And I just went ahead and verified it, testing it on the other transformations. So 49. This was, what is this? Cosine squared minus sine squared, negative sine cosine, -2 sine cosine times cosine, 2 times sine cosine, and then cosine squared minus sine squared theta. All of that, what does that mean geometrically? If it's multiplying by a vector, this is made up. I just made that up, 1 and 5. This one I couldn't figure it out. I didn't want to spend like multiple days. I've kind of started to struggle a little bit and then just say, okay, good enough struggle, move on to the next. I think to maintain volume and movement and progression. What I was seeing is that you can pull out a -1 here, and then I remember sine squared plus cosine squared, that equals 1. So really these can value to -1. And this, I think this is a trig identity, but I couldn't remember what it equals. Also, it seems very similar to the counterclockwise rotation, where there's a similar pattern where I think counterclockwise rotation is cosine, negative sine, sine, cosine. So these two are the same, just like the cosines, and these two are very similar, except this is a negation. So there might be something to that, but I'm just gonna use Quizlet tomorrow to figure out where I was missing there. True or false section then. A, basically standard matrix is a 2 by 3 matrix. What's the domain? The domain is r cubed, not r squared, I believe. Then C, is there a matrix transformation for which transformation of 2x equals 4 times the transformation of x? I said yes, because I think you can just plug in zeros, right? 0 vectors. Oh no. What was the question? Was it transformation? Either way, I think you can use all zeros. Yeah, I think you can use the transformation being all zeros itself, even though I didn't actually think about that originally. I thought the vectors were zeros. I think you could have a matrix, standard matrix being zeros, a zero matrix. So true standard matrix is a zero matrix. All right, and then the final true or false that I finished today basically was saying what? It was saying for every vector in Rn, the transformation led to a zero matrix is the standard matrix, then a zero matrix. I said I believe so. True. All right, that's it for today. Talk to you tomorrow. See you.